So hello everyone, welcome to the Gatewala. Welcome to the session of the revision through PYQ. So good afternoon everyone, very good afternoon to all of you. So as all of you guys know that the GATE exam is about to come and everybody is know that the PYQ is very important. PYQ play the very important role in the preparation for the GATE exam, because approximately the 60% question may be asked from the pattern of the PYQ. So today we are trying to cover the complete power system syllabus through the PYQ. We will try to learn the basic concept of the power system through the PYQ. So welcome all and good evening to everyone. Okay, so start with the transmission and the distribution topic. The first question is from the three-phase circuit. It is from the GATE 2018 question. A three-phase load is connected in the three-phase balance supply. That be the three-phase supply is a balanced one as shown in the figure. The phase voltage, A phase voltage, B phase voltage are given. No doubt the C phase voltage will lag the B phase voltage by 120 degree. And the angle are considered positive in the anti-clockwise direction. The value of R, so that the current that is flowing in the neutral is 0. You have to find out the value of resistance so that the current flowing in the neutral circuit is equivalent to 0. So it is already given that the supply is a balanced supply. Balanced supply means the magnitude of all three voltages will be equal and there will be 120 degree phase difference between them. So if Vn is given, the Vn is nothing but the 100 angle 0 degree. The phase sequence is A, B and C. So then VBN is 100 angle minus 120 degree. That means B phase voltage lag the A phase voltage by 120 degree. So the C phase voltage will be, the magnitude will be equal, but it will lag the B phase voltage again by 120 degree. So it is become minus 240 degree. Now this is star connected load. This current is a IA current, because here the phase current is same as the line current. This current is IB current and this current is IC current. And you can see, if you apply the Kirchhoff current law here, the current that is flowing in the neutral is nothing but the IA plus IB plus IC. So neutral current is nothing but the IA plus IB plus IC, the sum of all three current, that is the neutral current. Now it is given in the question that the current in the neutral wire is equivalent to 0 and you have to find out the value of R. Now see, what is the IA? IA is nothing but the voltage across resistance is Vn divided by R. So the neutral current IN is nothing but the A phase current, B phase current and the C phase current. A phase current IA, it is the voltage across resistance, that is the Vn divided by R. So it is a Vn divided by R. B phase current, this voltage is a VBN divided by J10, VBN divided by J10. And the C phase current, this voltage is VCN, VCN divided by minus J10. This is equivalent to 0. Now put the value of Vn, VBN, VCN. Vn is a 100 angle 0 degree, so 100 upon R. This is 100 angle minus 128 degree. J means 10 angle 90 degree. VCN is 100 angle minus 240 degree minus J10 plus J is 1 angle 90 degree and minus J is 1 angle minus 90 degree. All are equivalent to 0. Now solve this equation and find out the value of R, because 100 you can take common term, so it is become 1 upon R. If I take these two term right hand side, 1 upon 10 minus 210 plus 1 upon 10, because 100 will be cancelled out, minus 150 minus 240 plus 90 plus 150. Now the 1 upon R, add these two terms, 0.1 angle of minus 210 it is minus 0.086 plus j 0.05 I. Now 0.1 angle of minus 150. Minus 0.086 minus j 0.05. So 0.05 will be cancel out. So the 1 upon R, 0.086 into 2, 0.172. So the resistance will be inverse of 0.172. So 1 upon 0.172, it is a 5.813. So approximately it's a 5.8 or 5.7, or this is a right option. Clear? Okay. Now move to the next question. It is a GATE 2017. The nominal pi circuit of the transmission line is shown in the figure. The series impedance is Z and X. The value of Z is given. See the unit. The unit of Z is ohm, means Z is nothing but the impedance. And this X is also in the ohm. That means it is a reactance. It's not admittance, because the unit of admittance is mho, but its unit is the ohm. So it is a reactance. That means if I find out its value is 3300 ohm. Now the magnitude of characteristic equation of the transmission line in ohm will be. So what is the characteristic impedance? It's nothing but the under root of Z and Y. Z is nothing but the total series impedance and Y is nothing but the total shunt admittance. So series impedance is given. It is a Z. Z is Z only. Now what is the Y? Y is a total admittance. The total admittance means this is a Y by 2 and this is also Y by 2, because the total shunt admittance is equivalent to Y. That means the Y by 2 here, we have to find out the value of Y by 2. Now its value is given in the reactance term. That means its inverse is given. If X is 3300 ohm, that means in term of admittance, its value is 1 upon 3300 mho. If I convert this reactance into admittance, it will be 1 upon 3300 ohm. And this is admittance Y by 2. This is nothing but the Y by 2. So Y is nothing but 2 upon 3300. 2 upon 3300. So y, I got the value of x as well as z as well as y. Z is 100 ohm, just take only the magnitude 100, and y is 2 upon 3300, 2 upon 3300. Now find out the value of ZC. 100 into 3300, 406.20, 20 ohm. Good afternoon, everybody. Are you getting my point? This is given in the term of reactance, so I will convert this reactance into the admittance. Inverse of reactance is admittance, so its value is 1 upon 3300. Now we generally take the total admittance is equivalent to y. So this is a y by 2 and this is a y by 2. So y by 2 is equivalent to 1 upon 3300. So y will be the 2 upon 3300. Clear? Okay. Now come to the next question. In a 400 kilometer long transmission line, the series impedance is given. Ohm per kilometer means it is nothing but the pure length impedance. 0 plus j 0.5 ohm per kilometer. And shunt admittance, it is also per kilometer. So pure length admittance is nothing but the 0 plus j 5 micromho means 10 raised to the power minus 6 mho per kilometer. The magnitude of series impedance of equivalent pi circuit of the transmission line will be. Basically, it is a long transmission line. If you have to find out the magnitude of series impedance of equivalent pi circuit of the transmission line. Now, what is the long transmission line? The ABCD parameter. In the long transmission line, the ABCD parameter is nothing but the cos hyperbolic gamma L, ZC sin hyperbolic gamma L, 1 upon ZC sin hyperbolic gamma L, and this is the cos hyperbolic gamma L. No need to mug all the formula. Some formula you can immediately drive here. Now, what is the ABCD parameter of pi network? I am this assuming that the impedance is the Z dash and the admittance is a Y dash. So 1 plus Y dash upon Z dash by 2. This is nothing but the Z dash, Y dash, 1 plus Y dash Z dash upon 4 and 1 plus Y dash Z dash upon 2. This is my ABCD parameter of pi network, equivalent pi network. I have assumed that the total admittance is a Y dash and the total impedance is Z dash. You have to find out the magnitude of the series impedance, that is nothing but the Z dash. Y dash by 2, Y dash by 2. So I have to find out the value of Z dash. If I compare these two, the Z dash is nothing but the ZC sin hyperbolic gamma L. So the Z dash is nothing but the ZC sin hyperbolic gamma L. So you have to find out the value of ZC as well as the value of gamma. ZC is nothing but the under root of pure length impedance and the pure length admittance. So real term is 0, it's a J 0.5 and this is J 5 into 10 raised to the power minus 6. J and J will be cancelled out. So under root of 0.5 into 10 raised to the power 6 divide by 5, 316.227, 316.227. 227 ohm. Now, what is the gamma? Gamma is nothing but under root of Z and Y. It's a J 0.5, J 5 into 10 raised to the power minus 6. So, J will be come outside of this square root 0.5, 5 into 10 raised to the power minus 6. Zero 0.001581. Clear? Now, gamma L, if I multiply this gamma by L, L is nothing but the length. So, J 0.001581. The total length of transmission line is given, that is a 400 kilometer. So, 400 kilometer multiplied by 400 kilometer, it has become J 0.632. J 0.632. Sir, I am confused sometime to identify the phase voltage and the line voltage in the given question. See, in the three-phase question, whenever the data are given in the three-phase, the given data is always the line quantity. That means the given voltage will always be the line voltage, the given current will always be the line current, and the given power will be always be the three-phase power. So, in the three-phase system, the given quantity is always the line quantity until unless it is mentioned that it is a phase quantity, you will always assume it is a line quantity. Clear? Even if in the three-phase question, somebody is asking what is the voltage, you will always reply in term of line voltage only. So, by default, always assume it is a line voltage. Clear? Okay. So, now the value of Z dash is nothing but the ZC sine hyperbolic gamma L. This is my gamma L, J 0.632. Now, we all know that the sine hyperbolic J theta is nothing but the J sine theta only. So, it has become J sine theta. ZC is 316.227. It's a simple J sine theta. Sine theta means, now you will assume this is in the term of radian. 0.62 in the term of radian. So, first convert in the calculator mode from degree to radian. Now, find out the sine 0.632 and multiplied by the 316.227. It is a 186.8. This is the Z dash. Clear? So, first you have to convert the mode from degree to radian in your calculator, then find out the value of sine theta. It is 0.632. See, how we classify that the transmission line is a long transmission line, short transmission line, or the medium transmission line. It is according to the overall length of the transmission line with respect to lambda. With respect to lambda, and the lambda is a 6000 kilometer if we assume that frequency is equivalent to the 50 hertz. So, any transmission line which length is above 200 kilometer, whether it is a 50 kilometer or 60 kilometer, for both, it would always be the long transmission line. And see, in the question, it is clearly mentioned that you have to find out the equivalent pi network. Suppose if it were the medium transmission line, then the medium transmission line would always be represented in the nominal T circuit or the nominal pi circuit. So, there is no question of equivalent pi circuit in the medium transmission line. Clear? Okay, now come to the next question. This is from the GATE 2018. Consider the two bus system network with given load as shown in the figure. All value in the figure are given in the PU. The reactive power supplied by generator G1 and G2 are QG1. See, this is the active and reactive power supplied by generator G1. This is the active and reactive power supplied by generator G2. The PU value of QG1, QG2 and the line reactive power loss Q loss respectively will be. This is a very good question. See how to find out this value of QG1 first. You can see here the reactive power generated by the generator G is nothing but the QG1. Now the sum of the reactive power is directly supplied to the load which is connected with the bus bar J5, and the remaining reactive power will be the sending end reactive power. So QG1 is nothing but QS plus J5. So to find out the value of QG1, we have to find out the value of QS first, the reactive power at the sending end, and then add the 5 here. Similarly, here the reactive power supplied by the generator 2 is the QG2. Now the reactive power coming to this bus at the receiving end is nothing but the QR. So QR is coming at this bus bar, QG2 is also coming into this bar, and the total reactive power that is going from this bus bar is nothing but the J10. So we can say the QR plus QG2 is equivalent to 10. So QG2 is nothing but 10 minus QR. Clear? So to find out the value of QG1 and QG2, we have to calculate the value of QS and the QR first. Now we are supposed to also find out the value of Q loss. What is the Q loss? The total losses in the transmission line. Suppose the transmission line reactive power that is coming is a QS, and here it is a QR. So the difference between the QS and QR is nothing but the losses of reactive power at the transmission line. So to find out the Q loss is nothing but the QS minus QR. Again we require only the QS and QR. Clear? So we all know in the formula of QS and QR we need the value of delta. Without knowing the value of load angle, we are not able to determine the value of QS and QR. So first let us find out the value of delta. How we can find out the value of delta? We can find out the value of delta in this type of question always from the data of active power. So see, now come to the active power. The active power generated by the generator G1 is 20. Out of 20 active power, this is in the PU value, the 15 active power has been supplied by the load which is connected at this bus bar. So 20 minus 15, the 5 PU active power will move from sending end to receiving end. Oh, now this is clear. This 5 active power will come here because this is my lossless line. There will be no active power loss in the transmission line. It does not have any resistance, it is having only reactance. So there may be the loss of the reactive power, but there would not be any loss of the active power. Now the 15 and 5, the 20 active power is going to this load. So power that is flowing from sending end to receiving end, active power is 5. So in a lossless line, because it is given, line does not have any resistance, so it is a lossless line. The sending end power or receiving end power, this is 5. It is nothing but the sending end voltage, receiving end voltage x into sine delta. So sending end voltage magnitude is 1, receiving end voltage magnitude is also 1, and the value of reactance is 0.1, into sine delta. So sine delta is nothing but the 0.5. So value of load angle is the 30 degree. Clear? Because we need to know the value of delta to find out the value of reactive power. Now come to the reactive power, QS. What is the formula of reactive power at the sending end? It is nothing but the Vs square upon x minus Vs Vr upon x into cos delta. So Vs is 1, this is 0.5, 1 into 1, again this is 0.5. Now this cos delta is cos 30 degree. So 1 upon 0.5, if I take it is a common term, 1 minus cos 30. Find out the value of 1 minus cos 30 and divide it by 0.5. 1 minus cos 30 degree. Now divided by the 0.5. It is nothing but the 0.267. So 0.267 PU. Clear? So it was not 0.5, no, it was 0.1. X is 0.1. By mistake, I took it as a 0.5. So this is 0.1. So 1 minus cos 30. 1.34. 1.34 PU. Clear? Similarly, we can also find out the value of reactive power at the receiving end. Its formula is the Vs Vr upon x cos delta minus Vr square upon x. I will use the power formula for the lossless line. Again it is a 1 into 1, 0.1 cos 30 degree minus 1 upon 0.1. 1 upon 0.1 cos 30 minus 1. So it is a minus 1.34. Now, what was my QG1? QS plus 5. So QG1, QS plus 5. QS is 1.34 plus 5. It is nothing but the 6.34. Now, the QG2, 10 minus QR. 10 minus QR. Now the value of QR is minus 1.34. So it is become 11.34. And the reactive power loss in the transmission line is nothing but the sending end reactive power minus receiving end reactive power. So 1.34 minus 1.34. 1.34 minus 1.34, which is nothing but the 2.68 PU. Clear? So 6.34, 11.34, 2.68. The C is the right option. Clear? Any doubt in this question? It's a very good question. Always remember, in this type of question, by using the data of active power, you need to first find out the value of delta, and then from the delta you can find out the value of reactive power. Okay, next one, simple question, gate 2008. An extra high voltage transmission line of length 300 km can be approximated by a lossless line having the propagation constant 0.00127 radian per kilometer. then the percentage ratio of line length to wavelength will be. That means you have to find out the value of ratio of the length of the transmission line to the wavelength. This you need to find out. So length is already given. The length of transmission line is already given. It's a 300 kilometer. So to find out the ratio, just find out the value of lambda only. So how we can find out the value of lambda? In addition to the length of transmission line, the phase constant beta is given. Now we all know that the beta is nothing but the 2 pi upon lambda. The value of beta is nothing but the 2 pi upon lambda. So from this I can directly find out the value of lambda, that is nothing but the 2 pi upon beta. Pi are in the radian and this is also in the radian. So 2 pi divided by 0.00127. Definitely I will share the PDF of yesterday Ma revision in the group. 2 into pi 0.00127, 4947. So length is a 300, it is a 4947.39. Zero 0.0606, that means the 6.06%. D is the right option. Okay, come to the next question from the reactive power. A load is supplied by a 230 volt 50 hertz source. The active power P and the Q supplied by the load is such that, see, a load is connected here. Load take the active power somewhere between the 1 and 2 kilowatt. It also take the reactive power between 1 and 2 kVAr. A capacitor is connected across the load for the power factor correction. So I have connected a capacitor here for the power factor correction. It generates 1 kVAr reactive power. The load is consuming, but this is supplying the 1 kVAr reactive power. Capacitor is supplying the 1 kVAr reactive power. So the worst case power factor after the power factor correction is, that means you have to find out the power factor in the worst case when the capacitor is connected across the load. How to find out the power factor? Now you can see here overall the power coming is here is nothing but the power P, because the active power is consumed by load only. It is consuming, the load is consuming, suppose QL, this is my QL, means the reactive power of the load, but the capacitor is supplying the reactive power. So the total reactive power that is coming through the transmission line is nothing but the QL minus QC, because the QL is consuming and the QC is generating the reactive power. Now you have to find out the worst case power factor, that means the minimum value of power factor. So the worst case power factor is nothing but the cos phi. The minimum value of power factor will occur when the value of phi will be maximum, because when angle is high, the cosine of the angle will be low. So we need the maximum value of phi. If phi is maximum, that means the tan phi will also be maximum. Because for 0 tan 0 is 0 and the tan 90 is infinite. So what is the tan phi? Tan phi is nothing but the reactive power divided by active power. QL minus QC divided by P. QL minus QC divided by P. PL. L means the load power. Now the PL and QL is a variable, but QC is fixed. QC is my 1 kVAr that is generated by the capacitor. Now we need the maximum value of tan phi. To get the maximum value of tan phi, the QL should be maximum and the PL should be minimum. That's all. Then only we will get the maximum value of tan phi. So maximum value of load reactive power is 2. So it is nothing but the 2 minus 1. And the minimum value of load active power, minimum value is a 1. So it's a 1. So phi is nothing but the 45 degree. Tan 45 is a 1. So power factor is cos phi, cos 45 is 0.707. See, no doubt the load reactive power is more than the capacitive reactive power. So this is a positive term. So this power factor will be the lagging power factor. If QC is more than the QL, in that case the power factor would be leading power factor. So it says 0.707 lag. Okay, now this. Come to this question, GATE 2012. For the systems on below, ST1 and ST2 are the complex power demand at the bus 1 and bus 2. If the magnitude of V2 is 1, then the VR rating of capacitor connected at the bus number 2. What should be the value of VR connected at the bus number 2? Yes. See, in this power system, only one generator is there. That means this generator is generating the total active and the reactive power that is required for the load. So one generator, one load is directly connected at this bus bar, but second generator is connected at the bus bar which is far from the generator, and it is taking 1 pu power. So this 1 pu power will be supplied by this generator only. So the power that is coming from sending end to receiving end will be the 1 pu. Clear? So active power that would come from the sending end to receiving end will be 1 pu, because it requires 1 pu active power. No doubt the capacitor does not require any active power. So by using this is my again lossless line. It does not have any resistance, it is only reactance. So from this I can find out the value of delta first. So first find out the value of delta. The P is the Vs VR upon X into sine delta. So P is 1, sending end voltage is 1, receiving end voltage is also 1. So 1 into 1. The value of X is 0.5 sine delta. So sine delta is 0.5 or delta is 30 degree. Clear? Now if I find out the reactive power that is coming at the receiving end, QR. Now the reactive power at the receiving end is nothing but the Vs VR upon X into cos delta minus VR square upon X. So it is a 1 into 1, 0.5 cos 30 minus 1 upon 0.5. So this is 1 upon 0.5 cos 30 minus 1. cos 30 minus 1 divided by 0.5. Minus 0.267 in term of PU. See, this is reactive power. Capacitor will supply the reactive power QC, and I have to find out the rating of capacitor only. And here the reactive power is equivalent to 0. So if I find out the total reactive power here, the QR plus QC will be 0 because this is a 0 only. So QR plus QC will be 0. So QC is nothing but the minus QR, 0.267. So the capacitor must be able to supply 0.267 PU. So it is a rating of capacitor in term of reactive power, 0.267 or 0.268. Okay. Come to the next question from the cable. Two single core cable has a total conduction resistance of 0.7. Conduction resistance means it is a resistance of a conductor, and their insulation resistance between core and sheath are 600 mega ohm and 900 mega ohm respectively. When the two cable are joined in series, the ratio of insulation resistance to the conductor resistance would be, that means this is my one cable. The cable is having conductor, and above the conductor there would be the insulation. So this is the sheath. This is one cable. Now the second cable. This is my second cable. Now the resistance of conductor of one coil is 0.7. This resistance is the 0.7 of conductor. This is a conductor and this is the insulation. So 0.7, and the resistance of conductor of second coil, second cable is 0.5. Now the insulation resistance means what? That is the resistance offered to the leakage current. This is the conduction current flow, the direction of conduction current flow, but this is the direction of leakage current flow. The leakage current will flow from conductor to ground. So the resistance of insulation here, it is 600 mega ohm, and this is a 900 mega ohm. Are you getting my point? Insulation resistance is nothing but the resistance between the conductor and this earth, because the leakage current would flow from this conductor to earth. Now you can see the conductor resistance are connected in series because their one end is connected together only. Their one end is connected together only. So total conductor resistance two resistance are connected in series, 0.7 plus 0.5, it is nothing but the 1.2 ohm. It's grounded, means it's grounded na. Resistance between this conductor and the earth, because it is the resistance offered to the leakage current. The leakage current would flow from conductor to earth. Now you can see this one, this and this end is connected, you can see directly here. This end is connected together because we have connected in series, and this end is also connected together. So 600 ohm and 900 ohm, they are connected in parallel because they are both end are connected together. So 600 and 900, the total resistance, insulation resistance will become parallel means 600 plus 900. 3 plus 2. So the R insulation is nothing but 1800 divided by 5. So 1800 divided by 5. 360. Now what is the ratio? Insulation resistance is 360 and the total conductor resistance is 1.2. It is 300. Clear? Okay. Now the next question. A lossy capacitor rated for operation at 5 kV 50 Hz is represented by an equivalent circuit of ideal capacitor in parallel of resistance. We always represent a lossy capacitor like this. Resistance and the capacitance Cp. The value of Cp is 0.102 microfarad and the value of resistance is 1.25 milliohm. Then the power loss and the tan delta of lossy capacitor operating at the rated voltage respectively will be. You have to find out the power loss and the tan delta. See, both are connected in parallel. So the voltage across Rp and the Cp would be same. Suppose the current in the resistance is IR and the current through capacitor is IC. Clear? Suppose this is my voltage. Now IR current will in the phase of voltage only. The resistance current will always be in the phase of voltage. This is my IR. But capacitor current would always lead the voltage by 90 degree. This is my capacitor current IC. So the total current that is flowing through the lossy cable, lossy capacitor is a IC. I. Suppose take it as a I only. It is a sum of IC and IR. The phasor sum of IC and IR. This is my I current. So angle between voltage and current, if I take it as a phi, the power factor angle phi. This angle is called the loss tangent delta. Delta is nothing but the 90 minus phi. Clear? Delta is always called the 90 minus phi. Now we have to find out the tan delta. The tan delta. Tan delta. Tan delta is a perpendicular. This is nothing but the IR. IR. Perpendicular upon base. This is IC. IC. The current through resistance is nothing but the V upon R. Current through reactance is nothing but the V upon XC. So it is become XC upon R. XC is what? J omega C into R. Omega CR 10 delta. Clear? So 10 delta is a loss tangent. Frequency is 50 Hertz, 2 pi f. Value of C and R is given 0.102 microfarad and 1.25 mega ohm. So this will be cancel out 1 upon or you can say 100 pi into 0.102 into 1.25. 0.024. पॉइंट 0.024 है, 0.024 है. Sorry, 0.0249 है. It's a 0.024 something. So 0.024 10 delta loss tangent. This is called the loss tangent. Now, what is the power formula? It's a omega C V square into 10 delta. Omega any 100 pi, C 0.102 into 10 raised to the power minus 6 V square. See, this is a 5 kV. 5 into 10 raised to the power 3 square into 10 delta 0.024. $19.226 something, approximately 20. It is a 0.025. C is the correct answer. Clear? Okay, now come to the next topic, the fault analysis. So the first question, IA, IB and IC is given. The phase B 0 sequence current is IB0 and the phase A current IA, and the phase C current is given. Then find out the value of IB. Okay, do it. See, We all know that IA0 is nothing but the 1 upon 3 IA plus IB plus IC. Now the IA0, IB0, IC0 all are same because the zero sequence quantities are same. So it is nothing but the IB0. You can say, so 3 IB0 is equivalent to IA plus IB plus IC. So we can find out the value of IB just by subtracting IA plus IC from 3 IB0. 3 IB0 means 0.3 angle of 0 degree minus IA. IA is 1.1 angle 0 degree, IC minus 1 angle 12 degree minus 0.1. 12 है 120 है ये. 1 angle 120 degree हुआ ना. Now 0.3 minus 1.1 minus 0.1 minus 0.9 minus 1 angle 120 degree. This is the value of IB. Now in all the 4 options, this is the 0.1 angle 0 degree, 0.1 angle 0 degree. So 0.1, when it will come, if I add plus 1. So IB is nothing but if I add plus 1 and minus 1, minus 0.9 minus 1 angle 120 degree. So if I add plus 1 and minus 1, plus 1 and 0.9, it is a 0.1. Because in all the 4 options, the 0.1 is common. And what is the minus 1 and minus 1 upon 120 degree? So minus 1 minus 120 degree. This is nothing but a plus 1 120 degree. So plus 1 120 degree two 40. कहाँ गड़बड़ हो रहा है? 0.9 minus 1 120 degree plus 1 minus 1. If I add 1 plus 1 angle 120 degree, minus 1, one angle 120 degree. It's clear. One angle minus 120 degree. This is so D is the right option. D is the right option. Clear? Okay. Now the next. If star side of star delta transformer is shown in the figure, it's excited by the negative sequence voltage. Then find out the VAB, lead VAB by 60 degree, lag 30 degree, lead 30 degree, or it is excited by the negative sequence voltage. Here we are applying the negative sequence voltage. Negative sequence voltage means the sequence will be A, C and B. A, then C and then B. VA, VC, VB. I am applying the negative sequence voltage here. Clear? A, C and B. Now we have to find out the VAB and small VAB. VAB. If I subtract VB from VA, that means if I add VA and minus VB, you will get the VAB. So this is the VAB. VAB. Now what is the small VAB? Small VAB is this. The A point potential with respect to V point potential, VAB. Now see, this VAB is in phase of this voltage, VA voltage. This VAB in phase of VA voltage. Clear? So VAB will be in phase of VA voltage. This will be my small VAB. So I can say the capital VAB lag the small VAB by 30 degree. VAB lag VAB by 30 degree. Clear? Because this and this are in the same phase. Okay, next one. The series impedance matrix of a short circuit transmission line is given. All diagonal element is a self impedance and the non-diagonal element is a mutual impedance. The positive sequence impedance is given, zero sequence impedance is given. You have to find out the imaginary part of Zm. What is the positive sequence impedance? It is nothing but the Zs minus Zm. So Zs minus Zm is given. It is a 1 plus J10. Zero sequence impedance is the Zs minus 2 Zm. It is given 4 plus J31. Now find out the imaginary part of Zm. Imaginary part of Zm. We have to find the Zm. So if I subtract Zs minus Zs 0 minus Zm, so it is become plus Zm 3 minus 3 minus J21. So Zm is minus 1 minus J7. Sorry, it is a Zs plus 2 Zm. Na? Minus 3 Zm. So Zm is plus 1 plus J7. So J7 is the imaginary part. Clear? Now, the next one. For a power system network with n node, Z33 of the bus impedance matrix is J0.5. The voltage at node 3 is 1.3 angle minus 10 degree. If capacitor having the reactance of J0.5 is now added to the network between node 3 and the reference node, the current drawn by the capacitor will be. Z33 is given J0.5, V3 is given. See, this is my power system, which is having the n bus. 1, 2, 3, like this. Now there is a one reference bus. Z33 of bus impedance matrix is a J0.5. Z33 is nothing but the Thevenin equivalent impedance at the node number 3. The voltage at the node number 3, that means the node number 3 voltage, it is also given. It is 1.3 angle of minus 10 degree. If a capacitor having the reactance J3.5 is added to the network between node number 3 and the reference node, now we are adding a capacitor here. So if I convert this, the Thevenin equivalent circuit, at node number 3. So this is my VTH, and the node number 3 voltage is already given, which is 1.3 angle of minus 10 degree. 1.3 angle of minus 10 degree. Thevenin equivalent impedance. The Z33 is nothing but the Thevenin equivalent impedance at the node number 3. So it is given J0.5. If the capacitor is now connected between the node number 3, suppose now it is connected capacitor, its value is minus J3.5. So find out the value of current. The current drawn by the capacitor. It is a 1.3 angle of minus 10 degree, J0.5 minus J3.5. So 1.3 angle of minus 10 degree minus J2.5, or 1.3 upon 2.5 minus 10 plus 90 degree. So 1.3 upon 2.5, 0.52. Sorry, say 3 only, no? 0.433 angle 80° is the right option. Clear? Okay. Come to the next question. The zero sequence circuit of the three-phase transformer is given. The primary winding is connected in the star, but its neutral is not grounded, and the secondary winding is connected in the delta. See, we have a 4 switches like this to get the zero sequence network of the three-phase transformer. The primary winding is star connected, but its neutral is not grounded, so it will be open circuited. It is for the delta. Secondary winding is delta connected, so this will be closed. So overall it is become open, and this is closed, and this open. Which one is correct one? C. C is the right one. C is the right one. Yes. No. How you can directly divide the voltage by the capacitance? Because see, any two terminal network can be connected into the Thevenin equivalent circuit. So in the Thevenin equivalent circuit, there is a voltage source as well as the Thevenin equivalent impedance. You cannot imagine the Thevenin equivalent impedance is equivalent to 0 because the other network is also there. Other buses are also there. There must be some impedance connected between the bus number 3 and the other bus. So we will find out the Thevenin equivalent impedance, and Z33 is nothing but the Thevenin equivalent impedance at the node number 3, like Z22 is nothing but the Thevenin equivalent impedance at the node number 2. So you have to take the voltage as well as the Thevenin equivalent impedance. Yes, do this one. Gate 2020. Cylindrical rotor synchronous generator has a steady state synchronous reactance of 0.7 and the sub transient reactance, that means the xt is given. Xt is the 0.7, but the xt double dot sub transient reactance is 0.2 pu. It is operating at the 1.J0 pu terminal voltage with the internal EMF of 1 pu. Normally, in the normal time, without fault. See, if I draw the per phase equivalent circuit of the generator, it is given its internal EMF, means its EMF is 1 plus J 0.7. And in the normal time when fault is not there, then the voltage at the terminal of alternator is nothing but the 1 plus J0. Normal time the reactance will be XD 0.7, X 0.7. Now, so what would be the value of current? The load current, no doubt some load would be connected here. So the load current is flowing, that it is nothing but the pre-fault current. So how to find out the load current? IL. The load current is nothing but the difference between these two, 1 plus J 0.7 minus 1, 1 plus J0, it's J0 only, minus 1 plus J0 divide by J 0.7. This is the value of my load current. So J 0.7, J 0.7, it's a 1 pu, 1 pu. This is my load current in the normal condition. Now, following a three-phase solid short circuit fault occur at the terminal of generator, the magnitude of sub-transient internal impedance would be, so at the time of load, this EG is become EG double dot, XT is become XT double dot, and XT double dot is 0.2. There is a short circuit here. So now what will be the IG double dot, EG double dot? EG double dot is nothing but 0 IL into 0.2 only. IL is 1, 1 is the 0.2. Sorry, VT will there be na, VT plus JIL XT double dot. This is the EG double dot. So 1 plus J IL is 1, XT double dot is the 0.2. So 1 plus J 0.2 EG double dot. Its magnitude is become 1.0198. 1.0198 pu. Clear? Now, this question. The positive, negative and the zero sequence impedance of the three-phase generator are Z1, Z2 and Z0 respectively. For a line-to-line fault with the fault impedance of ZF, the fault current is IF1, and IF1 is nothing but the K times of the IF. IF is the fault current with zero fault impedance. The relationship between ZF and K would be line-to-line fault. So for line-to-line fault, the fault current IF, when the fault impedance is not there, is nothing but the root 3E Z1 plus Z2. Only positive sequence and the negative sequence would be present here. But when we also take the fault impedance into account, it has become root 3 into E Z1 plus Z2 plus ZF. We will take only ZF. In line to line fault, we always take only the ZF. If the ground is involved, you will always take it is a 3ZF. Now, it is given that IF1 is a K times of IF. IF1 is nothing time K times of IF. That means root 3E Z1 plus Z2 plus ZF is K times of root 3E Z1 plus Z2. Root 3, root 3 would be cancelled out. Now, it's the K Z1 plus Z2 plus ZF is the Z1 plus Z2. What is the value of ZF? K ZF is Z1 plus Z2 minus K Z1 plus Z2. So, if you take Z1 plus Z2 as a common term, 1 minus K divided by K. A is the right option. No, it's a line to line fault, na? It is already given that the fault is a line to line fault. In the line to line fault, the zero sequence network does not come into the picture. You have to see which type of fault is given. You are using the 3 Z1 plus Z2 plus Z0, that is applicable only for the line to ground fault. You are using the formula that is applicable only for the line to ground fault. Okay, now come to the power system stability. A 20 MVA 11.2 kV 4 pole 50 Hz alternator has the inertia constant of 50 megajoule per MVA. Megajoule per MVA, it means it is a H. The input and output power of alternator is given. Then find out the acceleration in mechanical degree per second square. Mechanical degree per second square. See, what is the PA? Acceleration power is nothing but the input power minus output power. Input power is a 15, output power is a 10. So PA is 5 megawatt. Now to find out the acceleration, we know that the PA is nothing but the m into alpha. Alpha is my acceleration. So m is gh upon pi f or 180 into f. We have to find out in term of degree. So let's say 180 into f. G is a rating 20 MVA. So G is 20, H is 15, 1 into F. Megajoule second divided by electrical degree. This is in the term of electrical degree, always remember, not mechanical degree, it is in the term of electrical degree. So 300 divided by 180 into 50 hertz. So 1 upon 30. This is a 1 upon 30. So P is a 5 megajoule. M is a 1 upon 30 into alpha. Alpha is 150 electrical degree per second square. But I will convert this into the mechanical degree per second square. So how to convert this? Yes. How to convert electric degree into magnetic degree? We know 1 electrical degree. I'm talking about the degree, not angle. 1 electrical degree is nothing but the 2 upon P times of mechanical degree. See, it is not the angle. No, no, theta electrical is the P upon 2 times of the theta mechanical. But here I'm talking about the degree, 1 degree. So it is the 2 upon P. How much P? 4. 2 upon 4 mechanical degree. That is a 1 upon 2. So our 150 electrical degree, it is a 1 upon 2 times of the mechanical degree. Per second square. So it is nothing but the 75. Alpha is 75 mechanical degree per second square. Clear? Okay. This question. The two transmission line is connected and there is a mutual coupling. See, the current is coming out of this dot terminal, the current is coming out of this dot terminal. That means they are in the additive polarity. Now find out the maximum steady state real power. Now E and B. The maximum power is nothing but the magnitude of sending end voltage, magnitude of receiving end voltage V divided by overall equivalent reactance. You have to find out the equivalent reactance. It is having the self reactance as well as mutual reactance. Because the current is coming out of the dot terminal from both of these transmission line, they are in the additive polarity. In additive polarity. What is the X equivalent? Formula is the x1 x2 minus m square x1 plus x2 minus 2xm. For subtractive polarity, this minus would be replaced by the plus. So x1 x2 1.5 1.5 j 1.5 j, xm is nothing but the 0.5 j square. X1 plus x2 1.5 j plus 1.5 j minus 2 into 0.5 j square, sorry 0.5 j only. So 2.25 minus 0.25, 3 minus 2 1, 2 आ गया ये. So P max is nothing but the value of E V divided by 2. B is the right option. Clear? Okay. This one. 3-phase 2-pole 50 Hz synchronous generator has a rating of 250 MVA, 0.8 power factor lagging. The kinetic energy at the synchronous speed is 1000 megajoule. The machine is running steadily at the synchronous speed and delivering 60 megawatt power at the power angle of 10 electrical degree. if load is suddenly removed, assuming that the acceleration is continued for the 10th cycle, what is the power angle after 5 cycle? Put the formula. How to find out the power angle delta? You need delta naught plus 1 by 2 alpha t square. Delta naught is already given. The initial power angle is a 10 electrical degree. 10 electrical degree. So to find out the value of final delta, you need to calculate the value of alpha, that means the angular acceleration, and t, that time. Oh, 3 plus 1, 2, sorry. 3 plus 1, 2, 2 and 2, 1. So it will be the EV upon 1. Sorry. Now, how to find out the time for alpha? Alpha we can find out from m alpha equivalent to PA. PA is nothing but the input power minus output power. If load is suddenly removed, it is delivering 60 megawatt power at the power angle of 60 degree. Yani, that means the initially when the system was in the steady state condition, then the input power will be equivalent to the output power, and it is given the 60 megawatt. Now load is suddenly removed. If load is removed, that means the output power is become 0. It is become 0. So the acceleration power is nothing but the shaft power minus electrical output power. The shaft power is same 60, but output power is become 0. So PA is nothing but the 60 megawatt. This is 60 megawatt. Now M, find out the value of M. M is GH upon pi F or 180 into F in term of electrical degree. So I will take the 180 into F. Megajoule second upon electrical degree. The value of M is G into H. G 250 MVA. H GH, it's directly given 1000 megawatt. H is nothing but the kinetic energy divided by G. So GH is directly kinetic energy, that is a 1000 megajoule. 180 into F, 1 upon 9 megajoule electrical degree. Now find out the value of alpha. PA equivalent to M alpha. PA is 60, M is 1 upon 9 alpha, 540 electrical degree per second square, and we have to find out the answer in the electrical degree only. Now the oscillation will remain continue for the 10th cycle, but we have to find out the final angle only after the 5 cycle. So convert the 5 cycle into time. Now the frequency is 50 hertz. 50 hertz means the 50 cycle is equivalent to 1 second. 50 hertz means 150 cycle per second. So 1 cycle is equivalent to 1 upon 50 second. and the 10 cycle is equivalent to 5 cycle. I have to find out the final angle after 5 cycle. 5 upon 50, that is the 0.1 second. Now delta is equivalent to delta naught plus 1 upon 2 alpha t square. Put the delta naught. Initially it's a 10 electrical degree. 1 by 2 alpha is also in the electrical term. 540 into 0.1 square, that means 54 plus 2.7, 12.7 electrical degree only. .7 electrical degree. Clear? Okay, do this one. The synchronous generator shown in the figure is supplying active power to an infinite bus via two short lossless transmission line and is initially in the steady state. The mechanical power input to the generator and the voltage magnitude E are constant. If load one line is tripped at the time T1 by opening the circuit breaker at the two end, then it is seen that the generator undergoes a stable transient. Which one of the following waveform of the rotor angle shown the transient steady correctly? Yes. Which one? A, B, C or D? A. See, initially both lines are in the circuit. Suppose the reactance of one line is a X. So overall reactance will be X by 2 without fault. So without fault, the PAM is nothing but the E into V divided by X by 2. Suppose this is the E and this is the V. Then after opening of the fault, if one line is tripped at the time T1 and opening the circuit breaker, the two end undergo the stable transient. If one line is tripped, that means the power will become EV upon X, because the total reactance will become X only. X by 2, now it is a X. So if you draw power angle characteristic, initially it was this X by 2 is less, the PM will be high, and then this, suppose I am taking it as a PBM. So this is my PA and this will be my PB. PB will be less than the PA. Initially, suppose it is operating at this point. This is the initial point, present point. Now what happened after the trip? The PA will be reduced to the PB. So this will come here. Now it will move like this. it will move like this. So this is the acceleration part and this is the deceleration part. It will move around this point and finally it will settle here. It will settle here when the input power is become again output power. So the value of delta will increase. The value of delta will increase. So value of delta will increase. Initially this delta is less and the finally this delta will be more. A is the right option. Okay, now come to the load flow. The I and J are connected with the transmission line of admittance Y at the two end, which are the ideal transformer. Then turn ratio is given 1 upon Ti, 1 upon Tj. The bus admittance matrix would be see. This is the admittance of transmission line. If I refer this voltage here, the voltage will be transformed as per the turn ratio. So it is become Ti into Vi. So it is become the Ti into Vi. And current, suppose this is my current II. Here the current will be transformed inverse of turn ratio. It is become Ie upon Ti. Similarly, if I transfer this Vj here, according to turn ratio, it is become Tj into Vj. Tj into Vj. If I transform the current, suppose it is a Ij here at this point, this is become Ij divided by Tj, because the current will transform inverse of turn ratio. Now, I have already kept the effect of these two transformer, so I will draw only this one. So draw this line only. The voltage here is a Ti Vi. Here voltage is a Tj Vj. Similarly, here current is Ii upon Ti. Here current is a Ij upon Tj. Now, apply the nodal method. This current Ii upon Ti, it is nothing but the difference of voltage Ti Vi minus Tj Vj divided by impedance, and the inverse of impedance is nothing but the admittance, and this admittance is given. Clear? Impedance inverse is the admittance. So Ii is become Ti square Vi minus Ti Tj Vj. Y. Here Ij upon Tj, voltage between these two Tj Vj minus Ti Vi divided by impedance, and the inverse of impedance is nothing but the admittance Y. It will become Tj square Vjy minus Ti Tj VIY. I can write in this form minus TI TJ VIY minus TJ square VJY. So now write this in term of matrix form IA upon IJ VI and VJ. This is my admittance matrix. VJ VI, it is a Y into TI square minus TI TJY minus TI TJY minus TJ square Y. Which one is correct one? No, TI square Y. This one. C is the correct one. Clear? So whenever you see the transformer in this type of question, it is always better shift the voltage and current to one side of the transformer. Now you already taken the effect of transmission transform into the account. So just find out the node, you can write down the nodal equation at this transmission line only. Clear? Okay. A 3-bus power system network consists of the 3 transmission line. The bus admittance matrix of the uncompensated line is given here. If the shunt capacitance of all transmission line is 50% compensated, means its value is reduced to the 50%, then imaginary part of the third row and the third column element of the bus admittance matrix after compensation will be. It's a 3 transmission line, 3 bus and the 3 transmission line. 3 bus means it is having the 3 bus like this, and there will be the 3 transmission line like this. Now, in addition to the series shunt, it will also have the shunt admittance. Now, shunt capacitance of all line is 50% compensated. We all know if we add the first row element or the first column element, it would give the total value of shunt admittance. So total shunt admittance connected with bus number 1. The total shunt admittance connected with the bus number 1 is nothing but the sum of the element of first row. 7, it is a J1. Similarly, the total shunt admittance connected with the bus number 2 will be the sum of second row element 5 and 3, 8. Again, it is a J1. Third row element 9. Again, it is a J1. So they are 50% compensated, means its value is reduced to 50%, become J0.5. This is the old value and this is become the new value, J0.5, J0.5. They are 50% compensated, means its value has been reduced by the 50%. Clear? Now you have to find out the imaginary part of third row and third column. when we are changing the shunt admittance, it will affect only the diagonal element, because by changing the shunt admittance, the off diagonal element of admittance matrix will be unaffected. So only the diagonal element will be changed. Now this diagonal element is the j minus j 0.8. It was minus j 0.8. Now what happened? The shunt admittance is reduced by minus j 0.5. It is reduced by minus j 0.5. 0.5 minus 1. The change is a minus j 0.5. So change is minus j 0.5. So it is become minus j 8.5. Clear? The change is minus 0.5. It has been reduced. So reduced by 0.5. So it is become minus j 8.5. Now come to this question. In a 100 bus power system, there are 10 generator bus. There are 10 generator. In a particular iteration of Newton-Raphson load flow equation in the polar coordinate, two of the PV bus are converted into the PQ bus. That means the two number of PV bus is converted into the PQ bus. In this iteration, the total number of unknown voltage increased by 2, or the unknown magnitude is increased by 2. Tell me. The PV bus is converted into the PQ bus. That means my PV bus now converted into the PQ bus. What happened? In the PQ bus, the known quantity was P and voltage magnitude. The unknown quantity was Q and load angle delta. When we convert this into the PQ bus, the known quantities become P and Q, and the unknown quantities become V and delta. Now you have to tell how much the unknown voltage angle is increased and how much unknown voltage magnitude is increased. Unknown voltage angle. See here, the voltage angle is already unknown in the PV bus. In the PQ bus also the voltage angle is unknown. That means the unknown voltage angle does not change, because here the delta was unknown, here also the delta is unknown. But voltage magnitude, in the PV bus the voltage magnitude is known, but now the voltage magnitude is become unknown, because we have changed the two PQ bus into the two PV bus into the two PQ bus. That means voltage unknown number is increased by 2. Number of unknown voltage magnitude is increased by 2. B is the right option. The delta does not change, because the delta is unknown both in the PQ bus and the PV bus. Clear? Okay. Come to this point. This is the last to last year question. Identify the bus PQ and the slack bus, PQ, PV and the slack bus. The injected power is, sorry, the generated power is given, and the demand power, because no load is directly connected with this bus. So Pi and Qi is known here. So this is my PQ bus. PQ is known here, it's specified. Now bus number 3, infinite bus having the magnitude of 1 0 and angle of minus 15 degree. So here we know the voltage magnitude and the angle, so it is nothing but the slack bus. Here the bus number 3, sorry, bus number 1, a current source is connected such that the magnitude of bus 1 voltage is maintained at the 1.05. That means voltage is fixed. Voltage is fixed here by the current source, and the phase angle of source current is phi 1 plus phi 2. Okay. See, its voltage is fixed. Now we have a variable current source. So by changing the value of current, I can change the value of power. V is specified. We can also specify the value of current, mean the power can be specified here. So this will be the PV bus, the PQ bus, PV bus and the slack bus. Now come to the switch gear and protection wala part. A lossless transmission line with 0.2 reactance per phase uniformly distributed along the length of line connecting a generator bus to a load bus is protected up to the 80% of the line by the distance relay. Only 80% of the line is protected at the generated bus. The generator terminal voltage is 1 pu. This is a there is a no generation at the load bus. The threshold pu current for the operation of distance relay for a solid 3-phase fault is close to 80% is line is protected. So there is a source, a generator, bus bar, and there is a load. The total line reactance is the 0.2 pu. But we want, by using the distance relay, the 80% of the line is protected. That means if the fault occur in this 80% of line, then the distance relay should operate. So the total reactance is 0.5. So up to the fault point, this may be up to the fault point, Maya. I am not bothered above this point. So ZF is 0.2, 80%, 0.16. Now this is my 1. If I convert this into a single line diagram or impedance single phase diagram, it is 1 pu. Up to 80%, the reactance is 0.16. So the fault current is become 1 divided by 0.16. How much? 1 divided by 0.16 is 6.25. D is the right option. A power system with the 2 generators shown in the figure. The system generator bus in the transmission line is protected by the 6 overcurrent relay. Assuming a mix of directional or non-directional relay, appropriate location, the remote backup relay for R4R. Actually, this is not there. Now tell the backup relay for R4R. Near the source, there will be the non-directional relay, and yes. Now, what we know that the relay near to the source is a non-directional relay. That means if the fault occur here, current flow in this direction or this direction, the relay should operate. So our non-directional relay is nothing but the R1 and R3 near to the source and R6. So we have a 3 non-directional relay. R1, R3 and R6. And the remaining relay R2, R4 and R5 is a directional relay. R2, R4 and R5 is a directional relay. Now it is showing what is the backup protection for the relay R4. If R4 does not operate, then which relay should operate? Suppose when the R4 will operate, when there is a fault between R3 and R4. Clear? Now see how the current will flow, how the fault current will flow here. The fault current will be provided by all source. This is the direction of fault current. Suppose if R4 is failed to operate, R is a directional relay which would operate when the current will flow in this direction only. So which relay should operate as a backup protection? Because for this we need to, the R3 and the R4 relay should operate. The R3 and R4 relay should operate, but R4 is failed to operate. Then which relay should operate? Will R5 relay will operate? See, will R5 relay will operate? Will R5 relay will operate? The R5 relay will not operate because it is my directional relay. It would operate when the current is flowing opposite to the normal direction of current, and this is the normal direction of current only, so it is not opposite to the normal direction of current. R2 is also do not operate because current is flowing is the normal direction of current only. But R1 will operate because it is a non-directional relay. It will operate whether current is flowing in the normal direction or opposite to the normal direction. R6 will also operate because it is also a non-directional relay. So if R4 is failed to operate, then the R1 and R6 will operate. R1 and R6 will operate. R2 and R5 will not operate because it is my directional relay. It can operate when the current flow only in the particular direction. Clear? Okay, this question. Three-phase transformer rated for 33/11 kV is connected in the delta and star as shown in the figure. The current transformer on low and high voltage side have the ratio of 500 by 5. Find out the value of current I1 and I2 if fault current is 300 ampere. The fault current is 300 ampere. Find out the value of current I1 and I2. No, R3 will operate definitely. See, when the fault occurs between R3 and R4, it is supposed to be that R3 and R4 should operate. R3 is operating. R3 is operating. Only the R4 is failed to operate. I am saying if R4 is failed to operate, then which of these relay will provide as a backup protection? If R4 will not operate, then R1 and R6 will operate. Clear? R3 will definitely operate. But due to some relay fault, the R4 is failed to operate. So in place of R4, the R1 and R6 will operate. Because R2 and R5 cannot operate, this is a directional relay. Yes, tell me. It's a 33/11 kV transformer. The CT ratio is 500 by 5. Outside of zone. The fault occur into the C phase only. See, the fault current is flowing only in the C phase. A, B, C. Take this as a capital A, capital B, and capital C. So the fault current will be the IC current only, na? If we neglect the load current, so this IE current will be equivalent to 0 because the current will flow only in the C phase. If this current is 0, then N2 upon N1, the out is nothing but the secondary side of current in the CT side. So I2, my CT ratio is a 500 upon 5. When current in the primary is 500, the current in the secondary will be the 5. But here the current is 0 because I am taking the output only from the A phase. And the fault is not in the A phase, so it is equivalent to 0 only. So I2 is equivalent to 0. This I2 is equivalent to 0. Now what is the I1? What is the I1? This is connected in the delta. Clear? No doubt, even the secondary side IA is equivalent to 0, this current will be also equivalent to 0. But here the current is not only this current, it is also this current. The C phase current is also there. Clear? This C phase current. The C phase current is, this is the 300. Now what is the per phase current? 33/11 kV delta star transformer. Primary side is delta, secondary side is star. Clear? 33/11 kV. This line voltage is 33. This is a 11 kV. Now if we find out in current in the C phase current. So per phase turn ratio, secondary, this is 33. 33 is 33 only. Per phase it become 11 by root 3. 11 by root 3. Now, if I transfer this 300 ampere here, N into I, capital NC into IC. Clear? Number of turn here is 33. I will find out the value of IC. Number of turn is 11 by root 3. And here current is flowing 300 ampere. 300 ampere. So value of IC is become 3. 100 by root 3. 3. 100 by root 3. Clear? This current is 0 and this 300 current here is converted into the 100 by root 3. So now what is this current? If you apply the Kirchhoff current law, it is the sum of this current or this current, whatever in the opposite direction. So this is 100 by root 3. So I1 is a secondary side of 100 by root 3. If I find out the value of I1, it convert 5 upon 100, 500 into 100 by root 3. One by root 3. So this is 1 by root 3 only. A is the right option. Clear? Because the fault is in the C phase only. A phase current is equivalent to 0. So here I2 is equivalent to 0. Now I will, according to turn ratio, I will transfer the 300 here. Will get the 100 by root 3. In the line side, this current is a sum of these two or the difference of these two, I and IC. 100 by root 3. Now transfer 100 by root 3 into the secondary side. Okay, now I come to this last question. Consider a stator winding of an alternator with an internal high resistance ground fault. The current under the fault condition are shown in the figure. The winding is protected using a differential current scheme with the current transfer of the 500 by 5. The current through the operating coil would be. Here, suppose this is my I1 and this is I2. So current in the operating coil is nothing but the I1 minus I2. ठीक है, और I2 minus I1. I1 secondary side current according to turn ratio 5 upon 400. The 400 current will convert into the 500. So now this is a current of 220. 220. Similarly, I2 will be 5 upon 400. 250. So current in the operating coil I2 minus I1. So 5 upon 400, 250 minus 220. That means 13 to 5 divided by 400, 0.375. C. C is the right option. Let's do one more question. This is from the admittance matrix. The three admittance matrix is given. You have to, sorry, the three bus is given. You have to find out the admittance matrix. The figure indicate the PU impedance. This is the impedance, not the admittance. So first convert into this impedance. 1 upon j 0.5. It's a minus 5j. So this is become minus 5j. 1 upon 0.08, 12.5. Minus j become plus j 12.5. Minus j 10. Do the inverse of every quantity, minus j into 10. GS and NR only one iteration may come. So see, what is the Y11? Y11 is nothing but the sum of total admittance connected with the one number bus, minus j minus 5, minus j 15. See, only from the one we can find out this value. Suppose if I find out the Y12, Y12 is nothing but the negative of admittance connected between 1 and 2, minus j5. It is a plus j5. So B is the right option. Let's do one question on this Newton-Raphson method. The PU power output of a salient pole generator which is connected to a infinite bus is given by the expression of, this is a non-linear equation, so you can solve this non-linear equation by using the Newton-Raphson method, where lambda is the load angle. Newton-Raphson method is used to calculate the value of delta for P equivalent to 0.8. The initial guess is 30 degree. Find out the value of delta after the first iteration. only this type of question may ask only one iteration. Otherwise, for gate exam point of view, the Newton-Raphson method or Gauss-Seidel method is not very important. They can ask only this type of question. See, I have to solve this question. 1.4 sine delta plus 0.15 sine 2 delta. This is equivalent to 0.8. Completely non-linear equation to find out the value of delta. Initial guess delta naught, it is a 30 degree. Yes, one theoretical type of question may come from the HVDC, no doubt. So this is my P. It's a 1.4 sine delta plus 0.15 sine 2 delta minus 0.8. We find out del delta is nothing but the P delta naught dP upon d delta at delta naught. So it is a 1.4 sine 30 degree plus 0.15 sine 60 minus 0.8. D upon d delta 1.4 cos delta plus 0.30 cos 2 delta cos 60 degree. The negative of this. You will get 0.0219 minus 0.0219. No doubt it is in the radian. So if you convert this into the degree, you will get the 1.26 minus 1.26. So delta 1 is nothing but the delta 0 plus del delta 0. 30 degree minus 1.26. कितना आ जाएगा 28.74. Clear? So these are the some question PYQ. We will again meet at 7 p.m. where we will discuss some new type of question that was not asked in the previous year. So in 3 hours 7 to 10 we will be discussing about the new type of question from all the topic. So do not forget to join us at 7 p.m. at the electrical gate wala channel. Till then, goodbye everyone.